Good morning, good afternoon, and good evening to all of you. Thanks for joining us. My name is Steve Kannengeiser. I'm the Global Marketing Director here at Brooks Instrument. Today we're going to share information about optimizing your bioprocess using mass flow controllers with onboard advanced diagnostics. These onboard diagnostics enable pre-programmed automation system actions to maximize process yields, as well as system throughput and utilization. Before we get into the details, I'll take just a minute to tell you a little bit about Brooks Instrument. Brooks has been a leader in flow measurement and control solutions for over 75 years. We have application knowledge and experience across many markets, including chemical, semiconductor, and of course, life science and biotechnology. We have a global footprint with sales and service around the world to support you and your customers wherever they might be. We also have redundant manufacturing for our mass flow products in the US and Europe. This redundant manufacturing provides many of our customers a level of comfort and supports a robust disaster recovery plan, which may be of interest in today's environment. Brooks has been a supplier of mass flow and pressure products to biotech applications for decades. We continue to deliver products with industry-leading long-term stability and other features to meet emerging biotech market needs. The advanced mass flow products that we'll focus on today bring new opportunities for automation that can have significant positive impact on your system reliability and process uptime. At this point, we're going to play a series of short pre-recorded video clips. The first clip is John Keir, one of our field service engineers. He's going to explain the system setup that we have and that we'll use for the balance of today's demonstration.
Hello, my name is John Keir and I work in technical services at Brooks Instrument. Today we're going to discuss some of the alarms, warnings, and other diagnostic capabilities of our SLA, Ethernet IP, and Profinet mass flow devices, as well as the increased turndown and near positive shutoff achieved by our devices with the biotech option. Here we have our tabletop reactor setup that we created to emulate a typical bioreactor with 5 of our SLA Ethernet IP mass flow controllers, or MFCs. These MFCs are configured for typical biotech gases: oxygen, carbon dioxide, air, and nitrogen. We installed upstream and downstream pressure gauges so that we can monitor the true pressure conditions around the devices. This will enable us to more accurately configure our alarms, warnings, and error thresholds for our specific system dynamics. Power is supplied through these M8 connectors, and Ethernet IP communications are through standard Ethernet cabling to the PLC. Downstream of our MFCs, we have shutoff valves for each device prior to the gas manifold, with the exception of the first device. This device is the biotech version, which eliminates the need for the downstream valve due to its near positive shutoff capability. In place of PLC control, for this demonstration, we're going to use our embedded web interface to configure the device and monitor the process. The MFCs are flowing into our tabletop reactor vessel, which you can see here.
Thank you, John.
All right. So with this simulated bioreactor system, we'll share a few thoughts on mass flow controller selection, setup, and automation. The first clip addresses the opportunity to simplify the bioreactor system design by taking advantage of an MFC with a wide turndown and near positive shutoff control valve. And we'll touch on the importance of proper system setup and device zeroing. The last 2 video clips will highlight restricted flow and backstreaming diagnostic alarms. These diagnostic alarms, when fully integrated into the bioreactor system, can improve the system reliability, improve overall uptime, and reduce the chance of a costly scrapped batch. This animation is showing what a wide turndown MSC can do for your bioreactor system. Turndown is the mass flow controller's maximum full-scale flow divided by the minimum controllable flow. That's the simple definition, but it leads to a deeper discussion on the usable range or usable turndown of the mass flow device. Stated simply, the device must have good accuracy, good signal-to-noise ratio, and good control stability at the bottom end of that turndown for it to be usable. The animation that we have running shows two similar systems. The system on the left uses a typical 50-to-1 turndown MFC to cover the oxygen flow range required. The system on the right uses one SLA series Biotech MFC with a wide 250-to-1 usable turndown. With this wide turndown, the user is able to eliminate one MFC from the system. This saves on system design, piping, automation, and device costs. It also makes the system inherently more reliable and reduces the reoccurring costs for maintenance, verification, and calibration. Now we'll share another video where Mark, another player on our technical service team, goes into a little more detail on the subject.
Hi, my name is Mark Thru, and I'm part of the tech services team here at Brooks Instrument. Today I'll be showcasing the wide turndown feature on Brooks's SLA mass flow controller, which can both simplify and improve your bioreactor system. So first of all, what exactly is turndown? Well, turndown is defined as the maximum usable controllable range of a device. For example, if you have a device with a maximum full-scale flow of, say, 100 cc's per minute and a minimum controllable flow of 2 cc's per minute, that would be a 50-to-1 turndown ratio. So turndown is going to be really important for customers in the biotech space or anyone running multiple processes or multiple programs on the same system. This is because one MFC is going to be able to handle a large number of different flow rates. This is going to reduce the amount of MFCs you have in your manifolds, the amount of MFCs you have in inventory. It's going to reduce validation time. Overall, it's going to save a lot of complexity, time, and money. So Brooks's Biotech MFC offers a 250-to-1 turndown, which is best in class. So what I'm going to be demonstrating today is I'm going to walk through running this 1 liter Biotech SLA and this 0.1 liter standard non-Biotech SLA. I'm going to run them both at 4 cc's per minute, and we're going to see comparable performance between the two devices, even though the Biotech device has a maximum flow rate that's 10 times higher than the standard device. At the end, I'm also going to mention the near positive shutoff valve that the Biotech device has, which allows you to completely remove the downstream designated shutoff valve from the system, which will further simplify your process. Okay, so the first thing I want to do is take this 0.1 liter standard device and run it at 4 cc's per minute so we can establish a baseline for what kind of performance we're going to expect out of the Biotech device after. So I'm going to open up the downstream shutoff valve downstream from the standard device. First, I'll set the device to its maximum full-scale flow rate, which is, of course, 0.1 liters per minute. As expected, we can see very stable flow. Now let's drop this down to 4%, which is 4 cc's per minute. Notice the excellent low-end flow stability, which is key for the initial vaccine inoculation stage. So what if your process requires a higher maximum flow rate while still maintaining the same levels of control and stability at lower flow rates? Under normal circumstances, you'd have to typically add another MFC to your system and connect the two with some sort of manifold. This is because standard MFCs usually run at a 50-to-1 turndown. But if you want to avoid adding additional complexity to your system, the Brooks Biotech MFC with a 250-to-1 turndown can help you run and capture even these higher flow rates while maintaining the same performance at lower flow rates. So next I'm going to showcase the 1 liter Biotech MFC and run this also at 4 cc's per minute, which is 0.4% full scale. First, let's run the 1 liter Biotech MFC at 100% full scale, which will of course give us a 1 liter per minute steady flow. Now I'm going to crank down the set point to 2% full scale, which is 20 cc's per minute. This is the normal limit of a typical MFC with a 50-to-1 turndown ratio. Next, I'll enter a set point of 0.4% full scale, which gives us a flow of 4 cc's per minute, the same as the device that we looked at earlier, even though that device had 1/10 the full-scale flow. Notice how this MFC provides excellent control and stability even at this very low set point. So the last thing I want to talk about is the importance of the Biotech MFC's near-positive shutoff valve, which allows you to completely remove the dedicated downstream shutoff valve from the system. So shutoff is going to be extremely important because obviously you don't want to overpressurize your bioreactor. You don't want to introduce the wrong recipe or the wrong process gases to your system. So for a standard non-biotech MFC, you're going to have a small amount of gas leaking by the control valve. We can easily demonstrate this by opening up the downstream shutoff valve, and you're going to be able to see a small amount of gas trickle through the system in the form of a bubble coming out once every 10 seconds. Okay, so now to next demonstrate the near positive shutoff valve on the biotech MFC. I'm going to turn off the gas flow from the standard device, and I'm going to set the biotech MFC to run at a 5% set point. Notice how you can see all the bubbles entering the system as expected as gas flows through the biotech MFC. Now I'm going to reduce the set point to 0%, so I'm going to completely shut off this near positive shutoff valve, and you can see the result is instantly no bubbles enter through the system because there's no gas leaking by the valve. So in conclusion, a manifold with 2 MFCs and 2 shutoff valves, like the one shown here, can be replaced by a single biotech MFC, which saves space, complexity, cost, and validation time.
Thank you, Mark.
Okay, next we're going to touch on zeroing the mass flow controller. This is an important step in the proper commissioning of any bioreactor system. If you have an improperly zeroed mass flow controller or an MFC that has poor long-term drift performance, it'll negatively impact the accuracy of that flow measurement. This animation shows 2 systems. The system on the left has an MFC with poor drift performance. The system on the right has a superior performing Brooks mass flow controller. Over time, the system on the left requires re-zeroing several times due to excessive MFC drift. A device with poor long-term stability will require more frequent zeroing, calibration verification, and recalibration, all adding to reduced system availability and higher maintenance costs. Brooks MFCs have industry-leading long-term stability, virtually eliminating the need to re-zero the device once it's installed and zeroed properly. If drift has been a concern for you in the past, we do have a zero drift diagnostic on board that can be programmed to raise an alarm when drift has reached a user settable threshold. You can also take advantage of the zero trending information that's stored on board the device. In this next video, Kyle Smith, our technical service manager, will review the proper zeroing of a device in more detail.
Hi, I'm Kyle Smith. I'm the Technical Services Manager with Brooks Instrument. Today I'm going to talk to you about the importance of the MFC zero in the bioreactor process. Good zero is crucial to ensure the MFC's accuracy is maintained. Inaccurate zero can lead to lost time tracking false leaks, or even worse, cause shifts outside of the accuracy specification of the GMP process. If accuracies fall outside of the GMP specification, it will trigger an explanation report to indicate why a product can still be run through the system, leading to burdensome administrative work. The following graph shows how a bad zero can directly impact the MFC's accuracy. The MFC will react to a bad zero by adding or subtracting the zeroed flow from the applied set point, which will show up as flow error during an accuracy check. There are diagnostic features in the Brooks Ethernet IP firmware that can alert end users to when a zero is recommended. It's important to note that the feature must be enabled and configured to a threshold that is optimal for each bioprocess. This screen shows a zero recommended warning that would typically come through the PLC, but in this case I'm reading through the Ethernet IP web interface. Brooks MFCs have excellent long-term zero stability. Before taking action on re-zeroing the MFC, it's important to account for the following variables that will impact the accuracy of the zero. First, ensure that the device has been warmed up properly and ambient temperature is stable and at actual operating conditions. Second, ensure that the system is final and the MFC mounting attitude is in its final orientation. And lastly, verify the system is leak-free to ensure leak flow is not being zeroed out. For this example, I've already verified that the temperature and mounting attitude are at steady state. I'm now going to leak check one of the nitrogen process lines. There are multiple leak detection methodologies out there, but for this example, I'm using a fluid leak detector for simplicity. I'm now going to leak check each process connection in the process line to ensure proper process connections have been made. If during a routine maintenance, a fitting was not connected properly, this is how a leak could look when caught during a system leak check. As you can see, the leak detection fluid is indicating a leak at the process fitting through the formation of bubbles. I'm now going to properly tighten the process fitting, and you will see the bubbles stop. I'm first going to close the downstream isolation valve to ensure there is not any flow going through the process line during the zero operation. It's extremely important to verify the pressure across the MFC valve has been equalized to the process pressure before executing the zero operation. I'm now going to open the MFC valve until the downstream pressure matches the upstream. Once I close the MFC valve, I'm going to zero the MFC. Zeroing can occur by communicating through the PLC, but in this case, I'm going to briefly depress the zero button on the side of the device for about 2 seconds. As you can see on the web interface screen, the MFC zero has now improved from roughly 2% offset to roughly zero. It's important to note that when there is a significant zero offset, a single zero operation may not be sufficient to achieve the desired accuracy. There's a feature in the Ethernet IP firmware called a bad zero warning that will identify if the first zero was insufficient. This warning can be configured to ensure the zero falls within the predetermined success band. If the zero falls outside of the success band, the warning will signal another zero is required. In this example, you can see the bad zero warning has been cleared, indicating a successful zero has occurred. We can now hand the equipment over to production with the assurance of long-term zero stability.
Thank you, Kyle.
All right, at this point, we're going to get into a couple of the automation opportunities. The first is the restricted flow alarm. The restricted flow might be caused by a faulty valve, faulty regulator, or a clogged filter. The Brooks SLA series mass flow controllers are able to identify when the set point signal and flow signal are misaligned. When this misalignment hits a user settable threshold, the device triggers an alarm. This is what we're showing in this animation, but you can take this a step further. The system can be programmed to read the alarms and take certain actions as a result. The first action might be an overall system check. What's happening with the pressure? What's the current shutoff valve state, etc. After a system check, an appropriate action may be programmed to occur. It could be to increase the pressure, open a valve that's not properly set, or some other action. By taking advantage of these automation opportunities, you may be able to avoid costly system downtime and potentially a scrapped process run. Our field service engineer, George Dury, will show this restricted flow alarm in this next video clip.
Hello, my name is George Dory. I'm part of the technical service team at Brooks Instrument. Today I want to talk about how you can utilize your Brooks Instrument thermal mass flow controller to potentially prevent damage to a bioreactor batch recipe. What I'll be demonstrating is an alarm called a restricted flow alarm. It's often referred to as a choke flow alarm. This alarm can alert you to the loss of flow due to pressure droop or other causes of restricted flow. This alarm can then be tied to your PLC control system, allowing you to quickly address the issue. I want to start by showing a few screenshots explaining how the restricted flow alarm works. As you can see, this shot shows a normally flowing mass flow controller. Valve drive and flow are smooth and steady. As you begin to see a loss of inlet pressure or pressure droop, the valve automatically opens further to maintain the desired flow. As the pressure continues to drop further, you can see that the valve responds by then opening to its maximum value in an attempt to maintain flow. At this point, the flow drops and the restricted flow alarm is activated. This will then alert your PLC control system. To address droop in a regulator, it is best to set the inlet supply pressure while flowing at 100%. This will assure the device has the required pressure to achieve all flow commands. The restricted flow alarm can be the result of a closed valve, a loss of supply pressure, regulator droop, increased back pressure, or other restriction in the flow line. Now let's watch a device in action. I'm going to simulate pressure drop by adjusting the inlet regulator until the device is affected and activates the restricted flow alarm. As you can see, the valve is responding to the pressure droop by opening further in an attempt to maintain the desired flow. As the supply pressure drops, eventually the device will be unable to achieve its requested flow and the alarm will be activated. The PLC will receive this alarm and allow for the problem to be quickly addressed. Now I will increase the pressure back to the correct value that the device was specified to operate at. On most bioreactors, it is approximately 35 psig. As you can see, the valve responds and correct flow is immediately reestablished and the alarm automatically resets. The restricted flow alarm is configurable by the end user. You can configure so that it activates at various levels of error band from the desired flow and after a set period of time.
Thank you, George.
All right, now the final automation opportunity that we're going to cover today, the backstreaming alarm. Backstreaming occurs when you get reverse flow from the bioreactor that can potentially back up into the mass flow controller. This can cause significant downtime and loss of a batch. In the animation, you can see some of the broth from the bioreactor flowing back into the gas line. If the backstreaming diagnostic is enabled, the mass flow controller will trigger the alarm and appropriate action can be taken. It would typically start with an automated system check. Depending on the findings of that system check, the system might take action on a valve, a regulator, or some other system device to eliminate the backstreaming situation. The faster a user or the system is able to react to a backstreaming alarm, the more likely it is for the system to remain operational. John Keir is going to share more on this backstreaming diagnostic alarm.
Utilizing and properly configuring the alarms, warnings, and errors for your process dynamics can provide valuable information to reduce the chances of human error or even help identify failures of another system component. I'd like to discuss another powerful diagnostic feature called the backstream error, which is configurable on our Ethernet IP and Profinet devices. First, let's define backstream. Backstream is a gas or liquid backflowing through the MFC. To put it another way, it's flow that is reversed from the normal flow direction. In a biotech application, this backstream condition can result in process downtime and costly repairs if fluid or other process material backflows into a precision device such as a thermal mass flow controller or meter. Avoiding this situation in the first place is key to preventing costly damage. There are 3 ways to access the error threshold configurations: through the PLC, the device's embedded web interface, or our Brooks Expert Support Tool or BEST software. The default backstream values are -20% of full-scale flow for at least 30 seconds. For this system, we change the threshold values from the default to -5% of full-scale flow for 5 seconds. Because gas will flow from high pressure to low pressure, a backstream condition could be caused by a drop in inlet pressure while the downstream is still pressurized. Some possible reasons for this drop in inlet pressure could be if the source is shut off when not in use, or a sudden increased demand for gas elsewhere in the building. Our recommendation is to build in mechanical fail-safes such as check valves to prevent backstream. However, a backstream could still occur due to a defective or missing check valve, and it's always a good idea to have some redundancy built into any critical system. Our recommendation is to build in these system precautions, but also configure an immediate process alert if this diagnostic appears. Service action is required, and in this state, it would fail a health check. As you can see, the flow signal is not reaching the set point, and in fact, we have a negative flow signal indication. You may see the valve drive increase until it reaches 100% because the controller is trying to adjust to the set point. However, at this point, we are at the mercy of the reverse pressure conditions around the device. After the configured threshold is met for the configured time, the backstream error is tripped. If the issue is quickly addressed through automation, for example, by automatically closing a downstream valve, damage and downtime can be prevented before personnel can even react to the indication. Because of the severity of the error and the need for intervention to correct the condition, this is a latching error and will not clear on its own. You will need to depressurize the system and check for contamination within the flow path, cleaning and purging as necessary before restoring the specified pressure conditions. Once everything has been corrected, you can cycle power to the device to clear the latched backstream error. You might also consider automatically checking the upstream valve or regulator status and pressure conditions through system automation.
Thank you again, John.
All right, at this point, we've touched on a range of subjects to help you select and commission your MFC. We've also shared a couple of examples of how the mass flow controller advanced diagnostics and deeper automation might be integrated into your bioreactor system. The Brooks SLA Biotech Series MFC has what you need for your bioprocess application. High turndown ratio, 250 to 1, extremely low leak rate valve, pre-calibrated biotech gas pages, all stainless steel wetted path, USP Class 6 ADI-free elastomers, material certs, and more. So at this point, I'd like to open it up to questions. As John said, type those into the Q&A in the webinar.
Excellent. For these questions, we'll be speaking to Joe Sipka and or Steve, whoever wants to field them at any given time, but I think we'll start with Joe, right, Joe?
Yep, no problem, Larry.
Excellent. So let me open up the Q&A and get started for you. The first one we have for you, Joe, is in such bio application, units are usually mounted in a cabinet, which tends to get pretty warm. It says here some competitors offer unique two-temperature calibration. What would be the Brooks argument on that? What's Brooks' take on the two-temperature calibration?
Sure, good question, Larry. Yeah, so understanding the ambient temperature in your environment is key. With our biotech MFC, we offer the four gases, four gas calibration, and we will calibrate it to match exactly what the customer's conditions are. And we do have the capability of changing the calibration reference as you're checking the calibration. So yeah, good question. And if there's more details required, you could reach out to me and Steve on that.
Yeah, I'll build on that just a little bit more. The Brooks devices have built-in temperature measurement and onboard temperature compensation. So if your ambient temperature is varying a little bit from the calibration temperature, the device does automatically compensate for that through the temperature compensation circuitry and measurement.
Excellent. Thank you, gentlemen. The next question I have for you is, do all of the Brooks Biotech MFCs have the advanced diagnostics capabilities and the web interface we demonstrated?
Yeah, good question, Larry. All of the Brooks MFCs do have some version of alarms and diagnostics. The embedded and our most up-to-date web server are available on our Profinet and Ethernet units on the SLA product series.
Another question I have for you. Thanks, Joe. Next question I have for you is, are there any limitations on what bioprocess control systems these can interface to? Can they work with the Emerson Delta V or the Sartorius DCU? Are you guys able to integrate to a large number of the providers?
Yeah, great question. Yes, from the Emerson PK controller, Delta V type of systems to Allen Bradley Rockwell to Siemens, Snyder PLCs. Yeah, we definitely have experience and work with different automation and IT departments to make sure it's a seamless integration with those things. So answer your question, yes, we have experience and a great tech support team to make sure that there's no issues with a startup.
All right, that's a great segue. This next question I have is that someone would like to know, can you guys provide on-site calibration and NIST traceable reporting to some of the, the core biotech hubs, South San Francisco, et cetera?
Yeah, definitely our core competence for Brooks. And I think, contacting us, finding who to contact on our Brooks website. We have invested in traceable metrology standards, and depending on the area, the NIST is the traceable in the U.S. For on-site calibration, and we understand that need, the workload capacity in the different pharma plants, and so we definitely have that on-site calibration ability to supply the as found and as left calibration certs.
Excellent, thank you. Okay, the next one I have has to do with, and this makes a lot of sense. If I have an older installation, and in today's world, older could be 5 years ago. If I have an older PD lab or a pilot plant installation, is there a migration or upgrade or retrofit? Choose your word. But is there a path forward where I can incorporate and introduce the SLA, the Brooks Biotech series, into my existing installation?
Yeah, great question, Larry. Yeah, and we get asked that a lot. Yeah, a lot of these devices have been running for years, and some of them have dust on them. They've been running so long. So yes, definitely the SLA Biotech series is a mechanical drop-in, so the same end-to-end footprint from our older model. So no mechanical changes are required. We also, like I mentioned, collaborate with automation IT teams if we do need to upgrade the protocol, change your protocol from a 4 to 20 milliamp to Ethernet IP or Profinet. But yeah, to answer your question, there's no mechanical changes going from the older series to the SLA Biotech.
So then along those lines, then where would you recommend someone go to kind of get more information about the process of doing so, like the integration or the automation recommendations and the path forward? Should they talk to you guys directly, or is there do you prefer they kind of start with the website? What's their best course of action?
Sure. Yeah, no, we have multiple avenues and paths to go contact us. I think our contact information is there. Steve and myself, feel free to reach out to us. We try to put as much information on our website with the manual software and guides, quick instruction guides, how to go set up and have a quick interface, along with the our interface files, our GSD ML file, and our EDS files for Ethernet IP. So yeah, we're definitely open to all type of discussions, assessments with the automation teams, and make sure that's ease of processing.
Fantastic. Thank you. That makes it so nice, that transparency and that accessibility. The final question I have for you guys was, has this presentation been recorded? And as I understand it, yes, it has. I believe they should probably reach out to either you, Steve, or Joe to follow up on that if there's any interest. Is that fair to say?
Yep, that's fine.
Yep, no problem.
Having said that, I want to thank everyone. That concludes our webinar, and thank you, everybody. Thank you to our presenters and everyone who attended for taking the time today, and we hope you found this highly informative. And if you have any further questions, please do not hesitate to contact Joe or Steve, and they'll be able to take care of you. Have a great rest of your day.
Thanks, everyone. Have a great day.